Right, now let's continue with our discussion regarding transformations, particularly the discrete Fourier transform DFT. Although I said that I don't want to go into further details, during the break I found a few web resources with some nice figures, so I want to go briefly through those things and show you a few of the properties of the DFT that we have been struggling to illustrate over here. Let me start my video as well. Okay, so the figures that I tried to draw was an attempt to make an illustration, but actually on the internet you can find very nice illustrations. So let me try to show you a few of those. For instance, yeah, it was here. Yes. So let me indicate whose these are. These are from Worcester or Worcester. I don't know how to even pronounce this thing. The Polytechnic Institute. Emmanuel Agu, and he seems to have some nice illustrations and a good presentation of the topic of the discrete Fourier transform and its extension to two dimensions. It starts with the normal discrete Fourier transform DFT, and it continues with the two-dimensional DFT. I particularly like these things, these illustrations, which actually correspond to the basis images, the two-dimensional shapes of the DFT. Of course, it's only showing the cosine part, the real part, but actually there's a phase-shifted version consisting of the sine part as well. This is not the discrete cosine transform we are talking about. We are talking about the discrete Fourier transform, and these are the basis images. As you see, they are on their way, and the coefficients with respect to one of them would correspond to the harmonic content of the image with respect to that harmonic. Those harmonics may be in any orientation and any frequency as well. It's interesting to note that when you combine all these regular waves, of course there are many more than this one. This is only a small set of things. Only 16 of them are available in this plot. But by combining these wave shapes, it's possible to come up with an image, for example, that looks like me in the picture that you see on the screen. My face. My face is not consisting of waves, but actually it is. And it's always possible to decompose into those things. And that is a fascinating property of the Fourier transform. And these are the basis images or the basis function of the two-dimensional Fourier, discrete Fourier transform, DFT, which are like this. So this is also another illustration of that. Now let me continue a little bit further to show you a few more things that I had been struggling to illustrate, but the illustration was already here all along. So, when you take the DFT of an image, a two-dimensional image, what you encounter is something that is similar to that you see on figure A here. So the corners of that figure A will exhibit larger values, and the center point of figure A corresponds to the highest frequency, pi by pi in the harmonic axis. Or in mesh plot, it looks like figure C, the one below. Okay, it looks like that. In order to have a better visualization, you would really like to have something similar to the figure in figure D. Okay, and the way to do it is to use FFT shift, as I have suggested in MATLAB, or figure B. So B and D are the more natural ways of looking at things, where the center point corresponds to the BC component, and towards the tail, it extends to higher frequencies along all directions. And so sampling the spectrum is the key here. Sampling in the figure, the spectrum is something desirable. If you take the DFT of the figure A, for instance, the house shape, it would look like figure B. And if you plot it in image format using MATLAB. But if you use FSD shift in 2 dimensions, then it is converted into figure C, which makes more sense, right? The center corresponds to the DC. That's something that we always want to do. And I found out that this PDF document also contains some very nice illustrative examples regarding what the DFT, centered DFT, would look like for some typical images. For example, the image at the left is house 0, house 1 kind of image. And look at the DFT of it. Okay, it corresponds to a line, with the peak value being a little bit larger in magnitude than the rest, and that is because the image is not zero mean. It's not -1 and +1. For digital images, you don't have negative values. It's always positive values. And when you add up all those positive values, naturally the DC components would be a little bit too much in magnitude as opposed to the others. So people prefer to not mesh plot or image show the Fourier transform in directly absolute value, but first they take the logarithm of it. In log scale, they prefer to present the Fourier transform. In log scale, those extreme values would be suppressed a little bit, and it would make more sense for the comparison. So this is the Fourier transform of house 0, house non-zero. A box, inside the box is non-zero, outside is 0. If you focus a little bit to this, you will notice that actually it passes through some zeros, and that is because of the sink. Notice that the box shape will have a rectangular shape profile. So those rectangular shapes will have a Fourier transform corresponding to a sink, and the sink is reducing in magnitude towards tail spot with oscillations. Every time it makes an oscillation, a zero crossing, you encounter that dark grid position, horizontally and vertically. So this is how the DFT of a box would look like. When you rotate the box, you also rotate the Fourier transform. You also rotate the DFT. This is an example to show it. The circle, it also exhibits a sink shape, but it is rotationally symmetric, as symmetric as possible because it is quantized, it's discretized. But that would correspond to a sink shape, which is also rotatively symmetric at the right-hand side. So DFT is also a sink that is decaying in magnitude. Notice that the negative values are also shown in absolute value as high values. So those large values are just decaying in magnitude towards the corners or towards the tail. And the center blob corresponds to the peak of that sink value. The zero crossings are the black circle. You see, it's not really very much circle because the circle here, as you see, is not a perfect circle. It's quantized around the corners because there's a finite resolution to this image, and that's the reason we don't see perfect sombrero shape, the Mexican hat shape, but instead we see some wrinkles and things like that. This I will skip because it corresponds to repetitions, and the circular convolution will make problems. So let's try to avoid those problems by windowing. That's the DSP issue, which is very important, by the way, but we are not going into the details of that. Instead, let's look at some examples of DSP. For example, the image on the left is the cameraman image, the famous test image, and the right-hand side corresponds to its DFT in logarithmic scale, probably. and you see some lines on the DSP, and those lines appear due to their corresponding perpendicular lines and edges that are found in the original image of the cameraman image. And if you low pass filter that by masking all the high frequencies and keeping or retaining only the low frequency region, this is what you will get after reconstructing or inverting the Fourier transform. In high pass filtering, you just eliminate the lower frequencies and keep the high frequencies, and you come up with something like the thing that you see on the right hand side. As you see, high pass filtering does not mean sharpening. It's something else. It's more like edge detection. If you want to sharpen, apply sharpening, the best you can do, or a good idea that you can do, is to add this high pass image onto the original image within a scale. Multiply the resulting image after inverse DFT, the black looking edge image, scale it by alpha, some parameter, and add it on the original cameraman image. That would emphasize the edge locations. It would look sharper. Okay, that's how you can, for instance, apply sharpening, not directly by high pass filtering. High pass filtering eliminates the DC coefficient and look at the image. It's not a sharper image. It's not even the image of the cameraman. It's only containing the edge. Okay, some various examples of high pass filtering, low pass filtering, etc. But I want to go to something else, which I also find very useful, and that is the frequency domain removal of some noise. We also talked about this, if you remember, in the previous week, but this was a very good example image, so let's use it. The image on the left-hand side has some periodicity and disturbance, so some additive or even maybe multiplicative periodic noise is appearing on the image. When you take the Fourier transform of that, what you observe are two bogus Fourier transform points corresponding to the cosine wave that we have, which is the ondula that is on the left-hand side. And they correspond to the red circled 2 points. We know that the two conjugate points on the DFT or Fourier transform axis, those two peaks, corresponds to the cosine. So we want to eliminate it. So what we can do is we can crop those points, make them 0, and take the inverse Fourier transform. But as you see, it's not only those 2 points, they have some shades, horizontally and vertically. Those shades are also containing some information, and it's because the right-hand side image is not the DF, it's not the discrete time Fourier transform, it's the DFT. DFT is the finite version of it, and because of that finite or bounded effect, we have some shadows which must also be handled properly. If you take the discrete time Fourier transform of the left-hand side image, then you would obtain only 2 peaks at the red circle position. So when you remove them like this, like the one at the left, with a notch filter, band reject filter, it will have this kind of right-hand side effect. As you see, most of the wrinkles have disappeared, but some residual effects are still remaining. Because if you look at, if you look closely around the notch lines, which are made 0, the dark lines correspond to making them zeros. There are still some shadows. The point spread function of that impulse is a little bit wider, and some light places, not completely dark, but some light places still remain, and those remaining places still cause some waves. We couldn't completely get to rid of the waves, unfortunately. You can do that. You can make more notching, but probably it would also deteriorate some details of the image. So there's a compromise about how to reconstruct. If you apply a bandage excitor in a circular way, it would reduce still some of the waves, but more waves will remain, as you see here. Okay. Some images at the top and their corresponding Fourier transforms. A narrow rectangular box, for example, corresponds to a sphinx shape with a wider block in the corresponding below Fourier transform, A versus D. I mean. So vertically, it's wider in D. If you make it thicker in D, then it makes a smaller thing in C. And if you make it even thicker and wider, the corresponding Fourier transform will be smaller, as you see in F. So larger images would make smaller Fourier transforms and vice versa. And they're also good for analyzing textures. For instance, the separation between the peaks in D, in figure D, is more separated, wider, emphasized dots, corresponding to the original texture in figure A to be actually a smaller and more dense figure texture. And B is a wider texture, so the points in E are a little bit closer to one another. It's more condensed. If you make the texture even wider, as you see in figure C, corresponding with the Fourier transform in F, the peak values, if you look at it closely, are even more condensed and near to one another. It's the duality relation between the Fourier transform and time domain signal. Here you see the rotation. When you rotate the texture, the Fourier transform points are rotated at the same angle. And lines and textures would make lines perpendicular to those in their Fourier domain, and you can see those things: A versus D, D versus E, and C versus F are some very nice examples. But many of the natural images, like A or B, will have a more uniform way of Fourier transform, where there is a peak in the center and it is mostly uniformly decaying towards the tails corresponding to higher frequencies. But for example, if it is not as natural as A and B, like the fingerprint image in C, which is very textured and there's a pronounced texture about it, its Fourier transform is quite awkward, like in F. Okay, and these are other examples of images versus their Fourier transforms. This is an interesting image. In the old days, when something is printed in newspapers, journals, and things like that, they were using this lower technology. They are still using this kind of a technology for dot printers, dot matrix printers. There is a matrix that is repeating its texture to give an average gray value. For example, the background. What's happening? This. So, excuse me. The background of the car is actually a light gray, but that light gray could only be obtained using black pixels and white pixels, because that's what a dot matrix printer does, to give it an average light gray. But because of that matrix pattern, if you try to take the Fourier transform of it, it looks like figure C. You see that you see those peaks of pattern, dot pattern, due to printing. And that's a good. That was a good example that I would really like to show you. And without an example like this, I would never be able to illustrate it. So I want to take this opportunity to show you this example. We are grateful to the original author, the professor of this presentation. We are using it. All right. So much about discrete Fourier transform. Now I can quickly proceed with the discrete cosine transform, abbreviated by DCT. Now, DCT is the real part of the Fourier transform. You can think of it like that. And it is also a real transform. That's why it's popularly used in applications of image compression, including JPEG. So instead of the e to the minus j blah blah kind of a transformation or a matrix in that format, we have a DCT matrix C. Let me see if I really have it. Well, I have an alternative way of making the representation. So let me write it that way. It's the DCT cosine transform of x of n in this format. This is x of k. So the original signal length is n, and its discrete cosine transform is also length n. And the cosine transform is equal to this summation. This is quite similar to the discrete Fourier transform, except the fact that we don't have this 2 cosine. We have 2xn. We have only xn times. And instead of this cosine that I'm going to write, we would have e to the minus j blah blah. But now we have cosine blah blah. What is that cosine blah blah? It's this pi over 2n k. Let me not put this in the parentheses yet. Yes, k times 2n plus 1. This is in the range where k is between 0 and n. Okay, and of course 0 else. Now this discrete cosine transform with this kind of an expression resembles something. Let's take a look at it and compare it to e to the minus j 2 pi over n k n. But there is a difference. The first difference is that this is cosine instead of exponential, so we are only dealing with the cosine part. We are not dealing with the j sine part, which is the imaginary part. We are taking only the real part. But not only that, the angle is also a little bit different. The angle in Fourier is 2 pi over n times k times n, and in the cosine transform, so let me put it like this, the angle is pi kn over capital N. Or I'm trying to write it as analogous as possible. Pi over n kn. Let me write it like this. Why did I say it that way? Because as you see, there is a 2n minus 2n plus 1 here. Sorry. If you don't think of this plus 1, just ignore it. It's like this 2 here and this 2 here can be cancelled. Consider it as pi k 2n over 2 capital N. Those 2's will cancel, and this is what you will have. That plus 1 is important, and I will mention about why it's important or why it is there. It is there to make sure that the discrete cosine transform basis does not become all equals, but it's slightly different. Because if you don't put it that way, when n is 0, which is the center pixel value or the sample value corresponding to x of 0. We have x of n. As n is equal to 0, it is x of 0. When n is equal to 0, it would make cosine 0. Cosine 0 is certainly 1. And regardless of the value of k, it will always remain to be 1, and that would be a problem. To eliminate that kind of a problem, and to make the transform matrix an invertible one, we prefer to use put a +1 here. Okay, that's why we are putting 2n + 1 in the cosine angle. But let's forget about that for the time being. Even the angles are different. This is 2 theta, whereas this is theta. Okay, the Fourier transform angle is twice the angle of the cosine, which causes this kind of a situation. In the Fourier transform, we know that in the DFT, we have a peak in the center towards high frequencies. It goes down to lower values, and then it goes up again. And this point corresponds to 2 pi, or capital N, if you wish, you can also call it. And this is n over 2, or pi. Okay, this is the black is DFT. So the cosine transform is half that angle, which means it is only from here to pi. So when you plot the DCT of something, the DCT plot would start with a large value and end with a small value, something like this. DCT will look like this in magnitude over n, or over k, let's put it this way, the new domain. And here, capital N, corresponding to pi. So Fourier transform and discrete cosine transform are different spans of frequency. DCT is only spanning from 0 to pi with the length of n, and the DFT, let me write it, DCT spans from 0 to pi with n samples, and DFT spans from 0 to 2 pi with n samples. But I'm telling you that actually the information that they contain are the same. So the DFT spanning from 0 to 2 pi with n samples is a little bit redundant then. Why is it redundant? Because it's complex values. It contains a real value and an imaginary value, which is too much. It's twice the information or twice the numerical value for transmission purposes if you're using it for compression, for example. For n samples, n real samples of signals, you're taking the Fourier transform. Now you have n complex samples. Of course, you can chop them off with more efficiency. You know why? But still, you have twice the number of data. Half of them for real values, half of them for imaginary values, because DFT is complex. So that's why they don't use DFT. But it is possible to use it. You have to be very careful. What you can do is you can make the DFT to span only from 0 to pi, which is this half of the data, the black data, and you can reconstruct conjugates. because we know that the left-hand side and the right-hand side are conjugates of one another. So knowing only the left-hand part of the DFT will let you know the right-hand part of it by its conjugation. So half of DFT contains sufficient information. So if you're using DFT for compression, you can use half of it in complex numbers, and half of it will contain n over 2 complex numbers, and n over 2 complex numbers would correspond to n real numbers. Just like n real numbers in DCT, now you have n real numbers in DFT as well. So both of them could be used for compression. But why would you bother with the conjugation, reconstruction business and all that? We have the discrete cosine transform. It's there, and it corresponds to the same information. So that's why people just use discrete cosine transform. And not only that, DCT also has a fast implementation, just like the discrete Fourier transform. There's fast DCT that we can talk about. Now, to give you an analogy between how to implement discrete cosine transform using discrete Fourier transform, I want to give you some side information. So relation of DCT to DFT, or you can think of it like this. If you have a machine that is capable of evaluating DFT, using that machine, will you be able to evaluate the DCT, whose formula is given here? Is it possible to do that? And the answer is a yes. And the relation is like this. You have, let's say, this signal. It's a 4-point signal. And you want to take the DCT of that 4-point signal. Let's call this signal X. Okay. And you want DCT of X. But you don't have a DCT machine. You only have an FST machine or DFT machine. What you really do is you extend it in a symmetric manner. You fold the signal, and you now have this, which is 8-point signal. I'm going to call it Y signal. Now this Y signal, except for a shift, is a symmetric signal. Now, for the time being, let's ignore that the symmetry is not around the origin. Let's assume that it's around the origin, it's symmetric around the origin. Imagine. For such symmetric signals, from Fourier theory, we know that the Fourier transform of real and symmetric signals, the Fourier transform of real and symmetric signals, are also real and symmetric. So the DFT of a symmetric Y, assuming that Y is symmetric, is also symmetric and real. And that's a very nice thing. It is telling me that the DFT is also consisting of some values, let's say like this, and it is symmetric. It's not symmetric around the origin, but it can be handled. So it's symmetric and real. This is the DFT. Let's call it capital Y. The capital Y is like this. It is real and symmetric. What does the DCT part that I'm looking for correspond to? It corresponds to only half of it. This part is the DCT of X. So the implementation idea is simple. We first fold our signal into a periodic extension, and then we use FFT, and the FFT will give us real and symmetric. So we are taking or grabbing only half of it, which is also real, and its size is the same size as our signal. Unfortunately, we have to take care of the shifting issues. So the X sub C, okay, this one, the DCT of X, is not really Y of K, but it is within the shift, like this. It's W sub 2n. I have to tell you what W is. It's a complex exponential expression, K over 2 times YK. And we have the definition of W here somewhere, because I don't want to, yeah, it's here. This thing, W sub A, for any A, where for this one it's 2n, A is 2n, is equal to e to the minus j 2 pi over A. Okay, so W sub 2n is e to the minus j 2 pi over 2 capital N, and W sub 2n to the power k over 2 is e to the minus j 2 pi over 2 capital N times k over 2, which means this is essentially e to the minus j pi over 2n times k. I think, if I'm not mistaken. I'm taking to the power of k over 2 altogether, and it makes pi over 2 capital N. Yeah. So, but this term is just due to the shifting. And without that shift, essentially what we are looking at is that the cosine transform is the same as the discrete Fourier transform's first part. Of course, this is valid. I have to put it correctly, between 0 and capital N minus 1, okay? Or up to capital N, the first half, where capital N is 4 for this example. Okay? This is a way to make the implementation of discrete cosine transform. Now, discrete cosine transform has one further interesting and important property, and it comes from the optimization of the transform. We haven't seen how to optimize the transform yet, but we will see that there is a statistically optimum transform that is optimized for a general class of signals with the same covariance or correlation structure. So if the signal is a random signal, but the random properties are stationary, so the signal is not changing its characteristics, for such a signal, you can always optimize your transformation. It may be a Fourier transform, it may be something else. I will write it like an example, but it's just the side information, and we will come back to the side information after we see the optimization. If your signal, a random signal, has this kind of a generative property. So x of n is equal to rho times x of n minus 1 plus noise plus an independent additive noise, zero mean, epsilon of n. Such systems are called autoregressive one systems, autoregressive. Why is it autoregressive? Because x of n is generated from the value of x of n minus 1. And the correlation factor between two consecutive samples is rho. That is the correlation coefficient between my past and myself. If rho is close to 1, it cannot be greater than 1, and it cannot be less than minus 1. If it is 0, it means it is uncorrelated. So it's like white noise. Every sample is uncorrelated from its previous past, completely doing some arbitrary attaining a value. That's the white noise. But if rho is not 0 but closer to 1, it means there's a strong correlation between me, my value, and my past value. Of course, they are different because there's an additive term of epsilon of n. That's the noise, the random noise. These are called autoregressive one sequences. And DCT comes out to be the optimum. We don't know how to achieve the optimum, but we will see that. It comes out to be the optimum transform for AR1 sequences as rho approaches to 1. So the stronger correlation signals can be best represented by DCT. How are we going to use this, or what can we do with it, with this information? It is telling us that if two pixels or two consecutive samples are very strongly related, and in natural images, that is the case. Look at an image of some sea here, and there's a grass mountain here, and some clouds and the sky over there, and this is the sea. So the sea is blue, and the grass is green, and the sky is also blue. Okay, this kind of an image. In the blue sky region, two consecutive pixels are very strongly correlated. If one of them is blue, the neighboring one is also expected to be blue. Or if you're in the region of a grass position, then two consecutive pixels would belong to the same grass. Or if it is the face of a person like this, then the pink skin tone and the neighboring pixel is also another pink skin tone. So it is very much obeying this autoregressive one with rho close to 1 characteristics, the natural images. But those natural images obey it only inside some small region. If that region is larger, then of course it doesn't obey the stationarity condition. Within the sky, it is stationary. Within the grass, it's stationary. Within the sea, it's stationary. But between the grass and the sea, there is no stationarity. So what they do is to come up with a cool idea of splitting the image into smaller, let's say 8 by 8 blocks. Let's split the image into 8 by 8 blocks. And apply DCT. DCT is the optimum, meaning that most of the energy will be pushed to fewer coefficients, and the other coefficients will have very small energy. I will show you, I will look for some illustrations from the internet for the next week, and I will show you what the DCT of a normal image would look like. You will see that the 0 by 0 corner will have a high value, and all the other values become very quickly becomes 0 or small values. So when you chop those small values off, how much error do you make? You make an error according to the square of those small values, which is also very small. So it's very efficient in compression. And we know that this compression technique which splits the image into 8 by 8 blocks. Within the 8 by 8 blocks, you can assume that it is stationary, the signal is stationary. So DCT will work fine. And when you do that, what you actually do is the famous JPEG. Okay, the JPEG compression technique, which splits the image into 8 by 8 blocks and applies DCT. And furthermore, it quantizes chops of some coefficients, etc. Of course, it's a compression technique. It's very complicated. Within each 8 by 8 block, several nasty things are going on, and it's very difficult to decode it. Actually, the data inside JPEG is a very interesting description of the image, and you cannot just write those values and create an image. You cannot do that. It's a complicated image file format, and it's just handling image 8 by 8 blocks, taking the discrete cosine transform, applying quantizations and chopping off, and further applying some zip-like compression techniques. So even the smallest 8 by 8 block is containing a lot of interesting information, and it's repeated for every 8 by 8 block, and that's how you literally paint or render the image. But the idea, all of those complicated things, come from the fact that discrete cosine transform is very efficient for autoregressive 1 signals as rho approaches the 1. Now, another interesting idea is that there may exist a discrete sine transform, DST. This is discrete cosine transform, DCT. The discrete sine transform is also an optimal transform for a completely different class of signals, which is autoregressive 1 as rho goes to -1. What does that mean? What is rho goes to -1 means? It means that the pixel value here is negatively related to the pixel value in its neighbor. So whatever my neighbor is doing, I'm doing just the opposite of it. If it is positively large, I will make it negatively large. If it is negatively large, I will make it positively large this time. So the relation is pure high frequency. For those high frequency signals or images like checkerboard images, things like that, discrete sine transform is optimal and you can use it. But we never use it. Why is that? Because in natural views, photos, we don't encounter those situations. The natural images are low pass. If you take the DFT of it, the DC coefficients will be large and all the high frequency coefficients will become smaller and smaller. So it's not good to use, it's not a bright idea to use the discrete sine transform, unfortunately. But if your image is very unique, you may prefer to use discrete sine transform. If your image is very unique in some other perspective, from another perspective, you may want to use other optimum transforms, neither Fourier nor cosine nor discrete sine transform. It may be a completely new class of transform that you may use. I want to stop at this point. I don't want to go into the other transforms for now. We will do it next week. But there are other digital-friendly, computer-friendly transforms which does not require any multiplication. So multiplier-free transforms also exist. We will see those things, rectangular shaped transforms. But I want you to look at the discrete cosine transform basis images. So I want to show them to you. I think I must have them somewhere. Just let's click on one of them. And I hope it will show. Yes. Now look at these. These are the basis images of 8 by 8 discrete cosine transform. You see that the first basis image on the top left corner is uniform like, and as you proceed on the right hand side, if you increase the frequency, the horizontal frequency, it becomes horizontally higher frequency towards the right hand side, but vertically the frequency stays almost zero. And then thinking of the transpose of it, if you proceed along the vertical direction, you see that this time the vertical frequencies increase. And all the others are like the cross or inner products of the two. For example, the 2 by 2 is 1001 like thing. But as you increase the frequency horizontally, you proceed further to the horizontal side, you see that the vertical frequency is only showing one oscillation. And towards the right-hand side, the frequency increases. Then you have vertically 3 oscillations in the next row, and towards the right-hand side, the frequency increases. If you proceed like that all the way, the 8 by 8 last one is a true checkerboard. 1 0 1 0 1 0, and then 0 1 0 1 0 1, and then again 1 0 1 0, etc. So this is how the basis looks like. So it's not waves, it's not only that, but it's more like the egg handlers, the egg cups that I was mentioning about in the previous lecture. Okay, it's different than the Fourier basis. This one is showing a checkerboard-like tendency. These are the 8 by 8 DCT basis images. And it's again an interesting fact that if you combine these basis images with proper scales and add them up, you can come up with any 8 by 8 image. 8 by 8 is a small image, so 64 basis images is enough to construct them, and these are all those basis images in the DCT domain. Okay, this is something that I would really like you to see. And in MATLAB, in the final exam or something like that, I may ask you to write some MATLAB codes to generate these things. Okay? So you may already try to construct the basis images. Okay. We will see other basis images, but only after seeing some few other image transforms, and then we will proceed with the optimality in the next week. So that's all I want to talk about for today. So the next week, you have your deadline for your take-home examination, but we will do the class again. All right. So please try to finish your examination until next week so that you will be able to attend the class. Because if you don't finish your examination, you will feel like, let me not attend the class because I need that time to finish the questions and answer the questions, which will be a pity because next week's lecture is something that I truly recommend, particularly the optimization. It's a very nice and neat way of doing an optimization. As scientists or engineers, it will be a very good example. So I strongly recommend that you attend it. But do not forget to finish your examination. So now let me ask you if you have any questions about the things that we have seen or about the exam or whatever. If you don't have any further questions, then yep. Was that a question? Maybe not. Okay. Anyway, you can always ask questions via email. Do not send your questions from the öğrenci bilişim sistemi, the information system. Directly send me emails, okay? If you want quick response, please write me an email. So I'm stopping now, and we will meet next week in the next course. And I wish you good luck for the examination. See you then.